Assalamu alaikum. I, Mirza Khidr Ali Beg from Earthquake Engineering Department is here. And thank you so much for having me. I am delighted to be here and I am so happy to be sharing my research work with all of you, which I have been doing from last 1.5 years under the sheer guidance and supervision of Dr. Aslam Fakir Muhammad from Civil Engineering Department and Engineer Adnan Rais from Civil Engineering Department as well. Today, I am here to make a presentation on my research work titled Tsunami Fragility Functions for the Low-Rise Reinforced Concrete Buildings in Coastal Region. My research work presentation is divided into three main sections. In section 1, I'll be sharing general overview and research motivation through the surveyed literature, which enables in deciding scope and objective of my research work. In section 2, I'll be sharing the characteristics of the selected buildings for my research work along with the methodology I adopted for the selected buildings in my research work. In section 3, I'll be showing the results which I have concluded from my research work. Moving on towards the section 1, in general overview, I'll be defining tsunami. Tsunami is a long high sea wave caused by an earthquake. And tsunami is also known as the giant waves, the killer waves, and the great waves in a water body. After that, I'll be sharing tsunami threat to the coastal belt of Karachi. The coastal belt of Karachi is more or less 67 kilometers away from the Makran subduction zone. And you can see in the attached figure. So the coastal belt of Karachi may experience a tsunami in the near future, which is subjected to an earthquake event in the Makran subduction zone. After that, in the general overview of section 1, I'll be sharing tsunami generation mechanism, which is when large earthquake occurs in the ocean areas, the sea floors rises or sinks. Accordingly, massive amount of water on sea floor also move up or down, and this movement spreads out in all directions in the ocean. The resulting waves called tsunami. The figure is attached for your better understanding for the easy perception of tsunami generation mechanism. After surveying, then from the surveyed literature, I found past recorded tsunamis caused by the Makran subduction zone. The Makran subduction zone triggered second deadliest tsunami in the Indian Ocean. There were 7 tsunamis recorded from 326 BC to 1945 with a year, source, and loss of life. Here I have compiled a list of historical tsunami caused by an earthquake in the Makran subduction zone. After surveying more literature, found more past tsunamis histories around the world, which caused many fatalities. There were 20 tsunami events observed around the world. Moving forward on the research motivation of section 1, I'll be sharing some damages to the building due to tsunamis. After observing damages, more literature reviewed to know the damaged states of the damaged building during tsunamis and then found some tsunami fragility functions showing damaged states. As you can see, some damages caused by the tsunamis, the timber framed residential structure floated, the 3-story residential building failed, out of plane failure of unreinforced masonry walls during tsunami. overturned reinforced concrete buildings, overturned timbered frame single family residence. After finding tsunami fragility functions, I'll define fragility function. Fragility functions indicate the probability that a given structure meets or exceeds a given damage state under the given level of demand parameters. After doing all literature review, we decided our scope and objective of our research work. I would love to share our scope of work and objective of research work. The scope of work is limited to investigate the response of low-rise reinforced concrete buildings. The low-rise we investigated were ground plus 3 stories building. And the main objective was to develop the tsunami fragility functions based on inundation depth and flow velocities. In section 2 of my presentation, I'll be sharing the characteristics of selected building. We selected 3 buildings, each of ground plus 2, which with different plane dimensions and different reinforcement in beams and columns. Here is a building 1, which is a 3-story ground plus 1 with a plan dimension of 26 feet 6 inches by 25 feet, having the following reinforcement in beams and columns. Here is the building 2, which is also a 3-story ground plus 2 building with a plan dimension of 45 feet by 60 feet, having following reinforcement details in the beams and columns. Then in the last, the building 3 is also 3-story building ground plus 2 with a plan dimension of 40 feet by 55 feet. In section 3 of my presentation, I'll be sharing all phases adopted in the methodology. I'll be going through by one from each phase. The phase 1 was modeling of all selected buildings using ETABS. You can see the building 1's 3D and plan view. Here is a building 2. Here is a building 3 with the 3D view and plan view. In phase 2 of methodology, we calculated the tsunami loads for the selected buildings as per the chapter 6 tsunami loads and effects of ASCE 716. We calculated load cases at global level, LC1, LC2, and LC3. On exterior and interior column for local level, on individual column, on exterior columns only LC3 plus reduced debris impact for the reduced debris impact level. Here you can see the tsunami load on building 1 at a global level. At a global level, we calculated LC1, LC2, and LC3 and found out the governing one out of LC1, LC2, and LC3. Similarly, for a building 2, we calculated LC1, LC2, and LC3 for global level and selected the governing one. Similarly, on a building 3, we calculated the same load cases as a global level. Then we calculated at local level for exterior and interior columns for building 1, building 2, and then for building 3. At local level, we calculated the tsunami loads on exterior and interior columns. Similarly, in the phase 2 of calculation of tsunami loads for the selected buildings as per ASCE 716, chapter 6 of tsunami loads and effects, we calculated the debris impact load for the reduced debris impact level for building 1, building 2, and building 3. In phase 3, the calculated tsunami loads were applied on a modeled building at global level, local level, and reduced debris impact level. On building 1, at global level, the governing was selected and applied as a UDL up to the maximum inundation depth, which is H maximum. Similarly, on a building 2 at a local level means on exterior and interior column, we applied the calculated tsunami loads on the model building as a uniform distributed load up to the H maximum, which is maximum inundation depth. Furthermore, in the last, we also applied tsunami loads on building 3, which is, at reduced debris impact level. We applied the LC3 as a UDL up to the maximum inundation depth and debris impact as a point at the tip of the maximum inundation depth. In phase 4 of methodology, we find out the story drifts of the model buildings at global level, local level, and reduced debris impact level by providing damage limits by a hazards manual. Here you can see for story drifts for a building 1, building 2, and building 3. We calculated story drifts of model building at global level, local level, and reduced debris impact level for each building. For building 1, for building 2, for building 3, but I am only showing for building 1 at global level, for building 2 at local level, and for building 3 at global LC3 plus reduced impact level. In phase 5 of methodology, developing a fragility functions occurs for buildings based on inundation depth, which is H maximum, and flow velocity U max. For building 1, building 2, and building 3 at global level, for building 1, 2, and 3 at local level, for building 1, 2, and 3 at global LC3 plus reduced debris impact level. Then in section 3 of my presentation, I'll be sharing the results which I have concluded. I'll be showing the fragility functions, tsunami fragility functions for the low-rise reinforced concrete buildings of the selected buildings. For building 1, building 2, and building 3 at global level, you can see which are based on flow velocity and inundation depth. Here on the right side, based on inundation depth, the blue curve is for the showing the slight damage in a building. Then the brown one or the orange one is showing the moderate damage in the building. The gray one is showing extensive damage in the building, and yellow curve is showing the complete collapse in the building. Similarly, you can see for building 1, building 2, and building 3 at local level, each curve is showing a specific state of damage, which is slight, moderate, extensive, and collapse. Similarly, for building 1, building 2, and building 3 at global LC3 plus reduced debris impact level. Thank you very much.